Hoodie Math coming at you with 5.2 slope fields. Calculus Maximus. Here we go. Let's get started. Example 7 maps the slope fields with their differential equations. So when you're looking through multiple graphs and equations, you might want to look for some easy ways out first. Let's try to draw some of these slopes. Looks like some kind of quadratic there. Just below it, just looks like a sine wave. Moving forward to letter B, looks like it's approaching some value here around 2. A lot going on here with C. Different slope fields everywhere. Here we know we have some kind of slant line approaching. So we're kind of coming in, flattening out, and then taking off. Same thing here. And then some kind of exponential growth that kind of looks like coronavirus. Let's do the corona first. Coronavirus. That would be your exponential growth. And that occurs everywhere in nature, probably modeling coronavirus. If you look at a graphing calculator, those are the slopes of an exponential. And you know that the function that would have came before it would have just been e to the x plus c. Again, just another exponential function plus constant shifted up or down. Some easy ones, I think, were letter D. That has to be the sine function. So I'm going to put letter something like that, or you can put letter D over here. Let's do both. Really messing up here, aren't I? All right, let's continue. What's going on here? Looks like it's some value y equals 2. We have something going on. So when y is 2, we get a slope of 0. That's got to be b. Let's put 3 up there. This is b. These guys are all done. All right, so again, you can look for slopes of 0. So here, slope of 0, that might be more difficult than some of these. Now this one only depends on x. If you think about the function beforehand, if you'd integrate that, 1/2 x squared, oh, that's a parabola. That has to be this one. And again, you look everywhere along here, and y's are not changing anything. It's only the x's. Everywhere at this x point, it's the same slope. At this x point, it's the same slope. X at this point, same slope. Y is not affecting this graph. All right, so we got a couple left. X minus y. So think about what's 1 minus 1 is 0. So anytime these are equivalent, we're going to get a 0 slope. Anytime these are equivalent, we're going to get a 0 slope. So it's got to be e, and by cross elimination, this one is 2. All right, so we've matched those all up. Hopefully you can kind of see why. You can look for different parts. I didn't explain all of the parts, but that does help. Again, you won't have any multiple choice on the AP test, but just practicing some other types of problems that you might see. All right, let's move on to example 8. On example 8, just looking for things again. Where can we find graphs? What are these graphs looking like? There's something going on here at 0. X at y equals 0. We don't have any slopes at y equals 0. Here, zeros is some kind of like shape like that, maybe a parabola shape. All right, so let's start. I notice that this graph is not dependent on x at all. There's no x values here. So when I look at the slope fields, I should be able to look across and the slopes will be the same everywhere. Oh, the slopes are the same everywhere. Not dependent on x at all. So 2 has got to be letter D. All right, let's find another one. It's probably a parabola, right? If you integrate 0.5x, you're going to get an x squared. Shift it over. B. Again, check some points. If I check 2, x equals 2, I'm going to get 1 minus 1 is 0. X equals 2. 1, 2. All right, moving on. Slopes of zeros, right? When I have a undefined slope, whenever y is 0. So whenever y is 0, I have a undefined slope, which they're not going to graph. Is this one defined at 0? Yes, it is. So C has got to match here. Another way to look at it is when y is 1, x is 0. We're getting a 0. X is 0 here, 0 here, 0 here. So this is going to be C. And finally matching up x plus y. So again, we have those zeros. Negative 1 plus 1. Negative 1, 1, 0. Negative 1, 1, 0. 1, negative 1, 2, negative 2, 3, negative 3. Anytime they're opposites, you're going to get 0. So that one is A. Moving right along. The slope field for a differential equation is shown at the right. Which statement is true for all solutions of the differential equation? 1. For x is less than 0, all solutions are decreasing. Well, let's look at this slope field. It looks like that. Anywhere you drop in, it's kind of doing this, kind of doing that. All right, so are all, when x is less than 0, so on this side of the graph, to the left of that side, are all those decreasing? And the answer is no, because quadrant 1, it's increasing. So that would be a no. Let's look at part 2. Oh, and I guess, although you don't need these strategies, right? All solutions level off near the x-axis. Leveling off, what does that mean? That means the slope is 0. Are all the slopes close, approaching 0 near the x-axis? And I would say yes. Here's the x-axis, and everything's getting closer to 0. So that's what it means to level off. So 2 is good, yes. So not C. So let's check last one. When y is greater than 0, anything above the x-axis, all solutions are increasing, and I would say yes, they're all increasing. So yes and yes. So it is 2 and 3. Example 10, a slope field for the differential equation dy over dx equals, we have a differential equation, we'll have vertical segments. When will it have vertical segments? Again, we're going to have vertical line segments when it's equal to 0. The bottom is equal to 0. Vertical tangent lines. So solving that, 2y equals negative 4x, y equals negative 2x. B. Moving right along. I'm only going to go through example 14, and that's all you guys have to do in notes as well. Example 11. All right, this one's a tricky one when you're reading it. I think after you read the first part and the second part makes more sense. So which statement is true about solutions y of x of a differential equation whose slope field is shown at the right? So when x is 0, that's what this means. X is 0. When y is going to be greater than 0. So at x equals 0, we have points here. Y is going to be greater than 0. Then the limit as y of x is going to equal 0. It's going to approach 0. So what they're saying is, here's the x-axis. They're talking about this region here. This is when y of x is greater than 0. So is it going to hit slopes of zeros as we go on forever and ever? And we just got to drop in anywhere above and see what's happening. So these are all going up, going up. Looks like they're approaching infinity and not 0. They're not leveling off. So no. not 1. 2. So now we're talking about this region here. This is between -2 and 0. And the slopes are approaching -2. So let's drop in anywhere x equals 0. We're dropping in here on the y-axis in this region. What's happening? Okay, so we're going down, following the slope, and then logistics curve, we're tapering off, quickly down, and then over. So anything that looks like it's approaching -2. So I'm going to say yes to that. So it's not A so far. It's not E. So let's try 3. What's happening in this region? It's going up. Oh, no, we're starting at 0 again, right? We're starting at 0. And we're seeing what's happening. All right, so we're approaching -2. We are not approaching 0. Right? Okay, so this would be a no. It is to only B. Moving on, example 12. So the rest of these I think are good examples. I got to those multiple choice hopefully pretty quick. Now we're just going to be graphing. You're looking for patterns. It's always highly recommended that you make a table. And look for patterns. That's really what we want to do. What is happening at 0, 0? Well, obviously, 0 times 0 is 0. We have 0 slopes. And once you see that pattern, you're like, well, anytime I have a 0, this is when y is 0, 0. So it looks daunting at first, but you'll find patterns that make this go quick. Again, anywhere we have a 0, if x is 0 or y is 0, it is equal to 0. 1, 1. So let's look at 1, 1. 1 times 1, well, this is going to be 1/2. Well, what about -1? This is going to be -1/2. All right, so anytime they're the same sign, we have a positive 1/2, a little bit flatter than a 1. So same sign here, and then other way, flatter, -1/2. Moving out, so now 2, 1. What happens at 2, 1? 2 times 1 is 2, divided by 2 is 1. And again, whenever you have opposites, let's say -2, 1, you're going to get -1. So 2, 1. Right 2 up 1, positive 1 slope, 45-degree angle. 1, -2, 1, +2, also same sign down here, same sign down here. Now -1s are going to be here, 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 and here, because you have a negative involved. And the last point we're going to use is the outside point, 2, 2. So 2 times 2 is 4, divided by 2 is 2. So again, positive 2 is a little bit steeper. Anytime the signs are the same and opposites, we're going to have a negative steeper slope. Okay, so we got the slope fields done. It looked tough, but just looking for those patterns, it goes pretty quick. Let f be the function that satisfies the given differential equation. Write an equation for the tangent line of the curve y equals f of x through the point y1. Use your tangent line equation to estimate or approximate the value of f of 1.2. So we're trying to figure out what f of 1.2 is based on an equation of the tangent line. So let's see what's going on at 1, 1. Here's 1, 1. If I had to draw a graph, it's flattening out here and then kind of going away. Same thing here. I'm kind of going steeper here, pushing away, steeper slopes. Maybe not that severe. So we know equations of tangent line for f of x will be f of x equals, well, some point. For now, it's f of 1 plus our slope, and then x minus 1. So f of x equals f of 1 is 1 plus m times x minus 1. There's our equation, and now we're going to approximate f of 1.2. So maybe I'll lock that in. Equation of the tangent line. Oops, I forgot a critical part, right? Before locking that in is the slope. I know the slope there. The slope at 1, 1 was 1/2. So probably should lock that in. Now we can lock that in. Locking that in. Okay. Now, f of 1.2. f of 1.2 is 1 plus 1 half 1.2 minus 1. Well, it's half of, what's the difference here? 0.2. So half of 0.2 is 0.1. So our approximation is 1.1. So f of 1.2 is approximately 1.1. Locking that guy in. Part C. Find the particular solution. So now we're going to solve the original differential equation. So leave any constants over here because you're always going to move them back. So just move the y over, 1 over y dy, and then move the dx over. So it's going to be 1 half x dx. And then again, we're going to integrate both sides. 1 over y becomes natural log. X becomes x squared, 1 half. 1 half times 1 half is 1/4. And again, plus some c value. To solve for y, we have to exponentiate. So we're going to exponentiate. And y equals e to the 1/4 x squared plus c. And again, we've talked about e to the c before. Based on our rules, we drop that c in front. And so it's just c e to the 1/4 x squared. That is our differential equation. Now, that's our general solution. We want to find the particular solution. So we're going to find a particular solution for 1.1. And then we'll use it to predict or estimate 1.2. So I'm just going to do that right here. So plugging in 1, 1. 1 for y, 1 for x. Looks like I have 1 equals c e to the 1/4. I would need to divide by e to the 1/4 on both sides. So that's what our c is. So now my solution for f of x is 1 over e to the 1/4. If you guys can see that. E to the 1/4 x squared. So interesting little function we have here. Let's plug this in, 1.2. Because now we're going to use our solution to find f of 1.2 exactly. All right, so when you plug this in, you get 1.16. You can see I messed up a few times above, right? 1.16. So how does that compare? So compare your answer from B to C. Well, from part B, we had f of 1.2 was approximately 1.1. In part C, we had f of 1.2 is 1.16. So this is smaller. It's an underestimate. And why is an underestimate? Well, if you look at this slope field, we know that the differential equation, the second, we know it's concave up. And since it's concave up, any tangent lines we draw below it So part B is an underestimate since the slope fields are concave up. Therefore, the tangent line is under the actual. Under the actual. Okay, so that's that. That's example 12. We're trying to get through a couple more here. Hopefully that made sense. Moving right along. Example 13. Again, we're only going to go through example 14. We're not going to do all of them. Just hitting the main key parts of the differential equations, the ones that are unique. All right, so we have dy over dx equals 1/2 x plus y minus 1. The first thing we're going to do is create a table to sketch out what is happening. So this one is a little more unique, probably because parts b and d. But let's go ahead and look at 0, 0. 0, 0, negative 1, right? So let's graph it. Negative 1. What else do we have? We have 1, 0. 1/2 plus 0 minus 1 is going to be negative 1/2. So negative slope, negative 1/2, flatter. All right, let's move over. Negative 1, 0. So negative 1, 0. It's going to be negative 1/2 plus 0 minus 1, negative 3 over 2. So it's going to be steeper than negative 1. Okay, let's move on up. Let's do 0, 1. So we get rid of the 1/2. So 0, 1. Oopsies. 0, 1 plus 1 minus 1, 0. All right, flat slope. All right, moving up. 0, 2. 2 minus 1 would be 1. All right, that was easy. 1, 1. So now 1/2 plus 1 minus 1. So you can kind of see that whenever y is 1, they're going to cancel that. So it's going to be whatever the x was. So if x is 1/2, we get a positive 1/2, flatter. And on this side, negative 1/2. All right, moving up. So when x is 1, we still have that 1/2. Y is 2. 2 minus 1 is positive 1/2. So 1/2 plus 2 minus 1 is going to be 3/2. Positive 3/2, so a little steeper. And on the other side, negative 3/2. Psych, positive 1. All right, cool. Hopefully I didn't make an arrow in there. Maybe I did somewhere, but I think I got them all. Okay, so we got the basics. Second derivative. So we haven't done too much of that, so that's good practice. Second derivative. We're taking the derivative with respect to x. So what's the derivative of x with respect to x? It's 1, so it's just 1/2. Derivative of y, we don't know. So we make it dy dx, and derivative of 1 goes away. So we do know dy over dx. It's what we started with. So we plug this back in. We combine like terms. 1/2 minus 1 is negative 1/2. So now we have the second derivative. When are these solution curves positive or concave up? Anywhere this is greater than 0. So anywhere this equation is greater than 0 or positive, it's concave up. So solving this, leave y there, move the 1/2 over. And this actually gives you the solution for part D as well, and I'll go over that in just a bit. So that is our answer. That describes all the solution curves that are concave up. C, let y equal f of x be a particular solution to the differential equation f of 0 equals 1. Does f have a relative min, max, or neither at x equals 0? Justify your answer. So if we're looking to see if it has a min, max, we'd have to know the first derivative. When is our first derivative equal to 0? And when is our second derivative? Positive, negative, 0. Right, so we're going to start here. dy over dx. So we want to know when dy over dx is. It's like I know dy. Oh, I do. That's what I want to know. When is that equal to 0? Right. So I'm checking it for this point. I'm got a little lost in my own sauce. All right, let's plug it in. So 1/2 times x plus y. What does this equal? Equals 0. So our first derivative equals 0. So since it equals 0, we know it's a min or a max. It's one of these. We don't know which one. So we go to the second derivative, because y, if it's concave up, it's positive, it's a min. If it's concave down, it's a max. Ooh, a little rough there. All right, we only got 2 more, Josh. Let's get through this. Or Mr. Olson, or eMath Hoodie, or eHoodie Math, whichever one you are. All right, you're hopefully not watching at this point. Do we have the second derivative? I don't think we do. Of course we do. It's right here. And what are we plugging in? We're plugging in 0, 1. So 1/2 times 0 plus 1 minus 1/2 is 1/2. So our second derivative equals 1/2, which means it's positive, therefore concave up. Therefore, it is a min. Justify. Ooh. F has a relative min at f of 0 equals 1, since dy over dx equals 0, and d squared y over dx squared is greater than 0. End statement. Moving on. Find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. There's 2 ways to go about this. We can go back to part B when we had a inequality and just make it an equal sign. Just change that to an equal sign, and therefore m equals negative 1/2 and b equals 1/2. If you've done that already, if you found the second derivative and set it equal to 0, that's what you have to do. Now there's another way of doing it. That's by looking at y equals mx plus b and taking the derivative with respect to x. Alright, so I'm going to do this one. Let's do this lighter color. We don't know the y, so it's just dy over dx. And taking derivative of this side, derivative of x is just 1, so we just get m. Do we know the dy dx? We do. We know it. It's the beginning, 1/2 x plus y minus 1 equals m. Do we know y? Yes, we do. It's mx plus b. Can we group these? Absolutely. And set it equal to 0. Differential equations. We can factor out a 1/2 plus m. And we can group these guys. And now we'd solve this. Glad you can see what I'm writing. We set this part equal to 0. So I just factored out a 1/2 plus m from the x. And we solve that. So 1 over 2 plus m equals 0. We want to know when that slope is 0, right? Because then it's a solution, so m equals negative 1/2. All right, and that's what we already had. Plugging it in here and setting that equal to 0, b minus m minus 1 equals 0. This is going to be positive 1/2 and negative 1 make negative 1/2 until you move to their side and it becomes positive 1/2. Those two. And that's what we already have. So 2 ways of doing it. Normally this is the way AP shows it on their solutions, but if you've already set the second derivative equal to 0, you can do it that way. Without the second derivative, this might be the only way to do it. Okay. Moving on. Last one. Example 14. Consider the differential equation. Again, there's a unique part of this one. That's why I'm going to do this, and then we've covered all the uniqueness. So, it looks daunting. It looks like there's a lot. Didn't even make a table for this one. We can just go through it. 0, 0. Oh, we have vertical slopes here. So, vertical slope. I'm going to draw them in there. Vertical slope. Do we have vertical slope there? No, we don't. We have a horizontal slope. We have vertical slopes anywhere y is 0. So, here, 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 and here. And normally the computers don't write those in when they do those. And then we have 0 slopes here. So that wasn't too bad. Okay, so 1, 1. Slope is 1. And here, 1. Oh, 2, 2, 1. Here, 1. Everything else, negative 1. And they're opposites. So getting done pretty quick. 2 for x, 1 for y. 2 over 1, positive 2. 1, 2, 1/2, but positive. Same thing down here. We go to negative 1, negative 2. It's going to be a positive 1/2. Then 2. We drop in over here. Now we're at the negatives, right? So we're at 2, negative 1, which is negative 2 slope vertical. And this is going to be a half slope. Same thing's happening here. Negative 2, 1. Negative 2 slope. Steep, flat. All right, kind of looks like one of those questions we did on the multiple choice. Sketch a solution curve that passes through the point 0, 1 on your slope field. 0, 1 in the slope field. Ooh, that's not 0, 1, that's 1, 1. Here's 0, 1. And there's a reason we're doing this question. Very good question. Going out. Going out. Cool. Neato. Find the particular solution. So now solve it. Move the y over, move the x over. Pretty simple stuff. Y dy, x dx. Integrate. 1/2 y squared equals 1/2 x squared plus c multiplied by 2. 1 y squared equals x squared plus 2c. Psych, just c. Because, again, the c just absorbs the 2. Just multiplication. It's a scalar move. But it does not absorb this square root. And don't forget the important plus minus. So that is our general solution. So now we want to find the particular solution with that initial condition when x is 0 and y is 1. 1 equals plus minus square root of x squared plus c. Well, we need to get rid of the square root, so we square both sides, getting rid of the plus minus. Didn't do that. Let's do this again. This is what I should have wrote. Okay, so we have to square both sides here, right? So that's just 1 equals c. So now our solution is y equals plus minus square root of x squared plus 1. But we can't have plus minus. Is it going up or going down? Right here it's positive, so it's not the minus, it's just the positive. And that's why it's important for these problems to make sure you know what your graph looks like. Because when you go down here to 0, negative 1, let's graph 0, negative 1. Here's 0, negative 1. Graphs are going down now. So when you solve it, for part D and E. So I just graphed it. Part E, we already have y equals plus minus x squared plus c. Plugging in -1. Well, when you square both sides, again, plus minus goes away, 1 equals c. C is still 1. So it's plus minus square root of x squared plus c, which is 1. And again, do we take the plus or the minus? Well, it's facing down this time. So in order for y to be -1, we have to have a negative there. So this is the final solution. For 0, -1, we do not use the positive. Where 0, 1, we use the positive square root. Here, negative square root. All right, that's been 14 problems. That's all I want to do on notes. You guys take care. This has been E Hoodie Math.